Hello all. In the last couple of videos related to the photochemistry, I had briefed you on the theories behind absorption, theories behind photochemical reactions, and a bit of kinetics related to the quantum yield. Now in this video, I shall brief you on the introduction or introduce you to the Jablonski diagram. Now Jablonski diagram represents the energy transformations that happens when a molecule absorbs radiation. Now we know that when a molecule absorbs radiation, it gets excited and goes to a high energy level and then comes down to the ground state, etc., etc. Through the Jablonski diagram, we will be discussing those aspects and we'll be representing it in a diagrammatic form. Now we know that in a photochemical reaction, we can represent the photochemical reaction as a molecule absorbs light, goes to the excited state, gets transformed to the product. So this particular reaction basically has two steps. The primary process wherein absorption of light happens and the molecule is getting going into an excited state, and in the secondary process the excited molecule is getting transformed into the product. Now in this particular reaction, it is the first step which needs the light, the second step doesn't require light. We have discussed this in detail in the earlier video. Now there is another type of reaction or process which happens when molecule absorbs light, and that is photophysical process, wherein there is no chemical change happening. Now in photochemical reaction or photochemical process, there is a chemical change. A is getting converted to P. Okay, the molecule A is chemically transformed to P. But in physical process, that's not happening. In physical process, the molecule A absorbs light, goes to the excited state, comes down to the ground state. Its original molecule is got back with the release of some amount of energy. So in photophysical process, there is no chemical change happening. It's just a physical transformation and the molecule is got back. So in a Jablonski diagram, we intend to depict what's happening when this particular thing happens. That is, when molecule absorbs light, it goes to the excited state, and then what happens? And we know that all these will happen, the excitation, when we say the molecule is getting excited, etc., it's actually the electrons in the molecule which is getting excited. So it's nothing but electron excitation. And we know that any chemical reaction involves electrons. It is this electron which is playing the important role. It may be transfer of electrons, or it may be sharing of electrons, or it may be migration of electrons, or it may be excitation of electrons. So the Jablonski diagram depicts this particular aspect. What happens when an electron gets excited? What are the energy changes happening, etc., etc. Now to know more on our Jablonski diagram, we need to know a few basic things. Now, we know that in every molecule, the electrons remain in the paired position. Alright, that is, the two electrons will be in anti-parallel position. Now, when we have the quantum mechanical aspects, and to explain the orientation of the electron around its own axis. We know that each electron spin around its own axis. And to explain the orientation of the electron around its own axis, we take the help of the spin quantum number. And when the electron is spinning in the anticlockwise direction, we have the spin quantum number -12. And when it is spinning in the clockwise direction, we have the spin quantum number +12. So the spin quantum number can have two values, +12 and -12. You already know about this. Now we have something else called the total spin quantum number, or the sum of all electron spins, that is designated as S. Now in this case, when the electrons are paired, S will be equal to 0 because you are adding plus half and minus half. So the total spin quantum number, or the total spin, angular spin momentum, we can say the total spin angular momentum is 0 when the electrons are paired. Now to have an idea about the stability and energy of the different electronic states, we bring in the term spin multiplicity. Now spin multiplicity is nothing but 2s plus 1. In this case, when the electrons are paired, we have spin multiplicity equal to 1. Remember, spin multiplicity gives us an idea about the stability and energy of the electrons, different electronic states. Higher the spin multiplicity, more stable will be the electronic state. Okay, remember that. Now this is one particular way of adding electrons, or maybe holding the electrons in the orbitals. Now when the spin multiplicity is 1, we say that state as singlet state. Okay, so we have a singlet state, wherein the spin multiplicity is 1, or wherein the electrons are paired, or wherein the electrons are having opposite spins. Now there can be another case also, wherein the electrons are having parallel spin, maybe clockwise or anti-clockwise, plus half. Both the electrons are having spin quantum number as plus half or minus half. In that case, the total spin will be equal to 1. You are adding these two spin quantum numbers. And the spin multiplicity will be equal to 3. Because when you put 1 here in the 2s plus 1 equation, you get it as 3. And this state, this energy state, electronic state, is called the triplet state. And we have said that higher the multiplicity, stable will be the electronic state. And so, triplet state is more stable. Now the reason why triplet state is more stable is because here the exchange energy is more. More the exchange energy, stable will be the molecule. Lesser will be the energy of the electronic state. Okay, so every system tries to increase its spin multiplicity. And we can say this, we have the Hund's rule which supports this particular statement. Now what does Hund's rule say? Hund's rule says that the electrons will be paired only after every orbital is occupied. So if we have 4 electrons in the p orbital, see here the electrons will be filled in this manner. First all the 3 orbitals will be filled, and then the 4th orbital gets paired to the first one, and not like this. So this is the actual way in which the electrons will be filled. Now see here, the multiplicity is more here when compared to here. Now here the multiplicity will be 1, while here you have 3. This will be in the triplet state. So this will be more stable. This will be energetically favored. This will be having lesser energy. Okay, so higher the spin multiplicity, stable will be the molecule. So triplet state has lower energy than singlet state. Alright, now what happens when this electron absorbs radiation? So the electron, we can put it as the electron is present in its singlet ground state, which can be represented as S0. Okay, the 2 electrons are paired in the molecule. Wow, now when light is absorbed, when you irradiate the molecule, the light will be absorbed by the electrons, and one of the electron goes to a higher energy level. It is getting excited. You can see here when the electron from the singlet ground state moves on to an upper, higher excited state energy level, the spin of the electron is retained. Okay, there is conservation of the spin of the electron. Now, since in this case also the two electrons are in the opposite spin, the multiplicity will be, spin multiplicity will be 1, and hence this particular excited state is called as singlet state. Okay, singlet excited state. So this will be, this particular energy level or electronic state is called as singlet excited state, as S1. In this manner you can have S2, S3 as you increase the energy level. Okay, as the electron moves on to the higher energy level. But the only thing is, when it must be in the singlet state, the spin of the electron must be conserved. That is, the electron in the ground state and electron in the excited state must be having anti-parallel spins or opposite spins. Now there can be another aspect also, another possibility also, wherein the spin of the excited electron and the spin in the ground state is parallel. Now that will result in the triplet state, wherein the spin multiplicity is 3. Now in that case, when the spin multiplicity is 3, the electrons are having parallel spin, same spin, and so this particular energy level or electronic level is designated as T1, triplet excited state. Okay, first triplet excited state. Alright, so this is the way the electron gets electronic transition occurs when it absorbs light. Now let us see what are the other happenings occurring here. Now if we represent the energy diagram of of the electronic states. Now when the molecule having the electrons, if we can represent the ground state of the electron as with this line, particular energy state wherein energy is always minimum or 0, and you can designate it as SO, S0 singlet ground state, and then the excited singlet state S1. Alright, and you have the two electrons, the electron pair over here with antiparallel spins, singlet state. You are irradiating it with light rays. What happens? One of the electron moves on, jumps to the singlet excited state, okay, with the same spin. Now this is in the excited state, this is having energy, and you know that no system will occupy higher energy level. It will always try to come down to the ground state or to the lower energy level. Now what are the different ways by which it can come down to the lower energy level? So the electron is getting excited to the higher energy level, singlet excited state. It can even go to S2, S3, etc. Now, as soon as it goes to the higher energy level, that the singlet excited state, it can come down to the ground state. Okay, it can come down to the ground state, and this process wherein the excited state comes down to the ground state is called relaxation. Alright, now relaxation can be in two ways, radiative relaxation and non-radiative relaxation. When there is emission of radiation, we call it as radiative relaxation. When there is emission of radiation, we call it as non-radiative relaxation. Now this, as soon as the electron comes down to the ground state, with the emission of some amount of energy, that's called phosphorescence. Okay? And there is another possibility wherein the electron from the excited singlet state loses its energy, wherein the spin of the electron is changed. Earlier it was in the anti-parallel spin, anti-clockwise spin, and now when it there may be the spin change, and it will go to the triplet state. So here the ground state electron and the excited state electron are having parallel spins. Hence, this will be in the triplet electronic state. Now, this triplet state will be having a lower energy and hence it will be lower than the singlet excited state. So this is called the triplet excited state 1. And this particular transition wherein the electron from the singlet excited state goes down to the triplet excited state is called intersystem crossing. ISC, intersystem crossing. We shall discuss this in detail in the next video. So this is also a non-radiative relaxation. While fluorescence is a radiative relaxation, intersystem crossing is a non-radiative relaxation. Now from the triplet excited state, the electron will then come down to the ground state, the singlet ground state. Alright, so from the triplet excited state, the electron will come down to the singlet ground state, and that can happen with the emission of radiation. And that particular phenomenon wherein from the triplet excited state, the electron is coming down to the singlet excited state, singlet ground state is called phosphorescence. Alright, so we have fluorescence and phosphorescence, which are the radiative relaxation phenomenon, and we have seen intersystem crossing, which is a non-radiative phenomenon, relaxation phenomenon. Now, in detail, we shall be discussing all these in the next video. Now, there's one more relaxation phenomenon, and that is the internal conversion. Now, what is internal conversion? Let us see. Now, if we draw the energy levels of the electrons in a more elaborate manner, the same energy singlet state will be having different vibrational levels. Here you can see different lines here, other lines V1, V2, V3, V4, V5, etc. They are all different vibrational energy levels. Okay, vibrational energy level 1, 2, etc. Okay, similarly, your singlet excited state will be having the singlet excited states 1, 2, 3 will be having different energy levels, vibrational energy levels. Alright, so, and even your triplet will be having the same. So this is actually, we'll be drawing this when we discuss Jablonski diagram in detail, we'll be drawing the energy levels in this pattern. Now there is one more non-radiative relaxation, and that's why I have shown you this one to explain that. Now see here, you have the ground state, okay, singlet ground state, and the electrons are absorbing energy, light, and then moving on to the singlet excited state. Here you have seen it as a single line, the energy level, singlet excited state are shown as a single line, but actually it is we'll be having various energy levels, vibrational energy levels. So the electrons from the zero vibrational energy level can move on to different vibrational energy levels of the same singlet state. Okay, now this particular V1 here, V1 of singlet excited state, if I show you singlet excited state as such, so here this will be V1. So the electron from ground state can move on to the lowest energy, vibrational energy level of singlet excited state, or the first, or the second, or the third, like that. Okay, so the electron which absorbs energy from can get excited to the first lowest vibrational energy level or the first vibrational energy level of the singlet excited state. Now that depends upon how much energy has been absorbed. So when you compare the electron in this energy level to the electron in the fourth vibrational energy level, the electron in the fourth vibrational energy level will be having a higher energy. So there is another way of relaxation is that this particular electron from the higher vibrational level can come down to the lower vibrational level of the same excited state, same electronic state. So here the electron from the highest vibrational energy level of the singlet excited state is coming down to the lowest energy level of the singlet excited state. This particular transition or electronic energy transfer or energy relaxation phenomenon is called internal conversion, which is vibrational relaxation. Vibrational relaxation. This is a non-radiative relaxation mode. Okay, vibrational relaxation, wherein the electron from higher electronic level, higher vibrational level, comes down to lower vibrational level of the same electronic state, same energy level. Okay, even here you can have, if you are giving little amount of energy, the electron from ground state lower vibrational level can move on to the ground state higher vibrational level and can come down to the ground state again with the emission of energy. Now this is non-radiative energy relaxation mode. Okay, now once this electron has been come down to the lowest energy level of the singlet excited state, it can undergo intersystem crossing, okay, or it can come down as fluorescence, okay, in the form of fluorescence with the emission of energy, etc. We shall be discussing this in detail in the next video. Alright, hope this is clear to you, the various types of relaxation modes, radiative and non-radiative relaxation modes, the triplet state and the singlet state, etc. Alright, so thank you for watching this video. If you have any more clarifications to be done, please feel free to ask me. Thank you.